Today we'll be giving a quick introduction to PyTorch for anyone that's unfamiliar with PyTorch at all. It's just a very quick dive into what PyTorch is. Then we're going to demonstrate how to build a transformer model with PyTorch with the transformers library from Hugging Face, and hopefully show that it's not that difficult. The resources nowadays are very, very good. Hopefully you aren't afraid to play around with the internals of a model then after this tutorial. And finally, we're going to show how to maybe adapt one of the models, specifically a BERT model in this case, to maybe achieve a different goal than just to create token embeddings, for example. By the way, anyone that's joined with a microphone, feel free to interrupt me at any point if the audio cuts out. No, and especially if you have any questions, if there's anything unclear. I don't have the chat open, so just yeah, let me know, speak out, and then we can hopefully have a nice interactive tutorial here. Okay, so getting started. If you want to, yeah, join in on the side, feel free to open the notebook in a different tab. But otherwise, yeah, just feel free to follow along. What are we going to do today? So the first part will be on PyTorch. And what is PyTorch? In my own words, PyTorch is a framework for deep learning. So it tries to make creating neural networks a lot easier, and fine-tuning or training neural networks really, really simple. And it's built on Torch, which originally was written in Lua, and then PyTorch came around when Python came around and tried to build a neural network training framework in Python, inspired by the Torch from Lua, and that's the history behind it. But the main part of PyTorch is there's two components, namely a tensor, which is a multi-dimensional statically typed array that's supposed to support very fast operations. We'll see a couple of examples for that. And the second part is a module, which is a composable class, so it's kind of hierarchical. You can nest a module inside of a module and stuff like that. But in the end, a module is a container that's just supposed to contain maybe some tensors as parameters or whatever, and then it defines how an input is processed into an output. So it's kind of what you'd expect a layer to be, and it's an abstract kind of container with which you can wrap some input and output. We'll take a look at examples of what those two things are. But first, to use PyTorch, we need to import it. So here's our first code cell, importing PyTorch. Now let's take a quick look at what a PyTorch tensor is. So in one sentence, it's a multi-dimensional statically typed array. What does that mean? Trying to put it into 3 points, it means we have a certain number of dimensions, and that's accessible via the ndim attribute in a tensor. It has a shape that describes how many elements the tensor has per dimension, and it has a fixed data type, meaning that just describes, yeah, what the values inside of the array or inside of the tensor has for a data type. For example, we could initialize, there's a bunch of different constructors for tensors, but we could initialize a random array using this constructor, torch.rand. And inside this constructor, we give the shape. So this means we have a three-dimensional tensor, which has two elements in the first dimension, 3 elements in the second dimension, and 4 elements in the third dimension. And yeah, let's run this cell and see what this looks like. So if we try to print the number of dimensions, we get 3. Our shape is 2 by 3 by 4. And our data type, by default, this constructor creates a float array, so our data type is float. And what does this look like in values, since we just have some random values here in this case? And PyTorch tries to make visualizing multi-dimensional arrays as easy as possible. But even in 3 dimensions, it's not that easy. Now it just tries for a 3-dimensional array or tensor, it tries to split the first dimension by a new line. So you can think of this as having 2 matrices side by side. So we have, yeah, the first dimension is 2, and then we just have 2 3 by 4 matrices of values. And that's pretty much what a tensor is. It's just a container for values that has a dimension or a number of dimensions, and then a shape dictating how these are arranged, and a fixed data type. And this should be, if you've worked with NumPy before, very similar to what NumPy ND arrays are, just a multi-dimensional statically typed array. On top of this, and that's what makes PyTorch tensors very, very useful, especially for deep learning, is it adds readily support for different accelerators, for example, GPUs. So you can just use these tensors directly on a GPU. And the second part, which is very, very handy, is it supports automatic differentiation, making it easy to compute the gradients which you would need for backpropagation when training a neural network. And just to demonstrate the GPU support, as a first step, we need to check in PyTorch if we have CUDA available. And if you're running this notebook and you don't, this prints false for you, at the very top here, you can change the runtime type. And by default, you get a runtime without a GPU, and then you just select one with a GPU. And then this should also print true for you. But since now we have a GPU available, we can simply move this tensor to a device. In this case, we just say at the tensor.toCUDA, and that means we move it to a GPU. So this tensor now lives or is stored in GPU memory. And what does this actually give us? Computations on a GPU are they're very good at computing highly parallelized operations. And so, for example, in this case, we're just multiplying two matrices, which are both, or 1000 by 1000 matrices. And this is a lot faster on GPU. So we just gain a lot of speed, parallelization, and things like that. So this is what this GPU functionality gives us. The second part, in my opinion, the really, really cool part of PyTorch, is it gives us automatic differentiation. What does that mean? Essentially, PyTorch, when doing any operations, which we can call a forward pass, that are done on a tensor, it will, in the background, store which operations were done. And for every operation, it also knows how to compute the gradient for that operation. And then after you've done all the computation, you can call a backwards pass on, for example, the final tensor, and that will call this whole computation graph that it's stored in the background and call all the gradient computations on that. And you can compute all the gradients along all of the tensors that were involved in this computation graph all at once without you having to do pretty much anything in the background. And to demonstrate this, let's look at a quick example. Let's pretend we're building our own little linear layer in PyTorch. So we have an input tensor that's just it's a vector of 5 ones. And then let's initialize a random linear layer. In this case, a linear layer would be a weight and a bias. This weight simply is a matrix, a 5 by 3 matrix that projects this 5-dimensional vector into 3 dimensions. So when we multiply the vector by the matrix, we'll have a 3-dimensional vector in the end. And then we have a bias that's just added on top of our output after multiplying with the weight. And so this is what our forward pass in a linear layer is. We multiply our input x with our weight matrix, and then we add our bias. This is what we would define as a forward pass. And then, for example, what if our desired output, our targets, would now be a 3-dimensional or a 3-element vector, a vector with 3 elements, just containing zeros. So we want to, for some reason, always project our input of 1s to an output of 0s. Let's just pretend that's our task. And when we could compute the mean squared error, for example, let's say our output is z, we subtract our desired target from that, square the result, and then compute the mean. That's our mean squared error. And if we run this cell, in this case, we initialized our weights and biases randomly, and then this is our output that we get, and the mean squared error of this output is 12.74, whatever. Now that we've done our forward pass and computed our loss, we can now call the backward function on the loss tensor, or it's a scalar value, but it's a 0-dimensional tensor. we can call the backward function. And this backward function, as we can see here, it kind of stored this whole computation graph of which computations have been done on the tensor. And if we call this function, we can then actually grab, or it in the background computes the gradients which are now accessible for all of the weights and bias, or for all of the parameters that were involved in the forward pass. So we can access for our W, for our weight, the gradient, and for the bias, the gradient. And these are then stored in these .grad attributes. So this is actually doing backpropagation from our loss through everything. And this can be more complex than just a linear layer. The PyTorch will compute everything for you in one go. And then just as a quick example, we could use these gradients to then do gradient descent. For example, if we just do 100 training steps in this case, we always do our forward pass, so compute our output, then we compute our loss. In each step, we need to zero the gradients every single time, otherwise they will accumulate. But then we compute our new gradients and then do gradient descent with some learning rate. For example, in this case, our learning rate is 0.01. So we just, since we're doing gradient descent, subtract the gradient times 0.01 of our learning rate. And then if we do this for 100 steps and just print the loss in every 10 steps, it seems like our model is learning to project the input of ones to zeros in the end. So this is the two cool attributes of PyTorch. You can use a GPU, and it has automatic differentiation attached to it. Note that all of this differentiation that's being done in the background, you rarely need to touch this when doing PyTorch, especially in some kind of practical applications. Just as a quick introduction, and yeah, in my opinion, it's nice to know how things work in the background. At least it's not just magic. You at least know what's happening, even though you don't need to touch it. Okay, that's a tensor. Our second very nice thing in PyTorch is the module. And what does this do? As mentioned in the beginning, a module is a kind of container that can contain some tensors as parameters. And in the forward function of a module is where you define how some input tensors should be modified or whatever, how they may interact with the parameters, and then how this module then outputs another tensor, for example, as an output. And just as an example, we could formulate our linear layer that we defined with some manual weights and biases up top in this way. So here, to have in an object-oriented way, we define our class, which is a child of the torch.nn.module. This is defining this as a container, as this module container. And then the constructor, we have some input dimensions and some output dimension that we want. And then we define our parameters as some random tensors that take the input and output dimension for the linear layer, and for the bias, just the output dimension. And then our forward pass is exactly what we did before. We just do, given an input x, in our forward pass, we do the matrix multiplication of our input with our weights, and then add our biases on top. And to initialize this layer, we can then just call the constructor, and we could then do the forward pass simply by calling using the linear layer as a function. This in the background will actually call the forward pass. The PyTorch module always routes a call to an instance directly into the forward function. So this is pretty much exactly doing what we did before manually. Now we just have this in a nice class hierarchy and object-oriented way, which we can then compose and things like that. Note that this linear layer that we defined here is a very, very common operation. And so PyTorch already implements this as just torch.nn.linear. And there's a lot of other different modules that are already predefined, some convolutions, some activation functions, and things like that. Mostly anything you'd ever need is pretty much already defined, except very, very custom stuff. Now, the nice thing about these modules is they are composable. meaning we can combine them, we can chain them, nest them into one another. And as an example here, let's define just pretty much a common multi-layer perceptron, and we just in this case call it a custom layer that again is a child of the torch.init module, and in this case contains two linear layers that receive some input dimension, and the first one just maps it to the same input dimension. Then we add an activation function in between, and then have another linear layer that maps it to some output dimension. And then in our forward pass, we call the different layers on our input and then return our output. So this is supposed to demonstrate you can compose these however you like. We could now add another module that uses these multiple layers, and in the end, through all these forward functions and PyTorch doing automatic differentiation, we can easily build a very, very complex network that will still allow us to compute the gradients of all the parameters in our network. And this is what makes PyTorch so usable and nice, and seems like why everyone has been moving to PyTorch. All right, this wraps up our quick introduction. Hopefully some people that already knew PyTorch learned a bit. Anyone that didn't, hopefully got a quick introduction into how things work. Now we will jump into Hugging Face transformers. So this is quite a big jump, I guess, in terms of complexity, because we're now jumping from simple layers to a very large type of network pre-trained transformer models, but hopefully I'll be able to show you that it's not as complex as you might think. So what is Hugging Face transformers, or the transformers library from Hugging Face? In a sense, at its core, it's just a repository of a lot of different implementations of various transformer-based language models. If you look into the repository, it's just a big folder of a lot of different model names and then containing the modeling code for these different transformer models. And around this, the whole Hugging Face ecosystem is wrapped, which, for example, has the model hub, which makes it easy to load some pre-trained weights and things like that. But in the end, it's just a bunch of definitions of how the models are defined. And to demonstrate that this is pretty much all that Hugging Face transformers is, let's try and re-implement BERT, a simple BERT model. Quick note here, we won't touch the tokenizer. Maybe that's a story for a different day, or how these models are configured. The documentation on both these things are actually quite nice, so feel free to read up on that in your own time. Also, one last final note, if some of the code that we'll be discussing now leaves out a few details. For example, we leave out dropout just to simplify a couple of things. So there may be slight differences if you use this code for pre-training or fine-tuning. Just use the official BERT implementation for Hugging Face if you want to do pre-training or fine-tuning. This just demonstrates how to implement it if you would like. Okay, as a conceptual quick overview, what is a BERT model? A BERT model consists of one embedding layer. This here, so we have some inputs and an input embedding layer that converts some tokens into vectors, and then adds some positional encoding on top. And then there's just a stack of how many layers you would like, a stack of transformer layers, which inside do some multi-head attention and some residual connections and some normalization. We'll take a look in detail into what these types of things are, but I'm sure many of you will be familiar with this visualization of a transformer encoder model. And this is pretty much all that BERT is. So an embedding layer and then multiple transformer layers. We will first take a look at this embedding layer, how this is implemented, and then take a look at the different transformer layers, how they can be implemented. So what does an embedding layer do? The embedding layer first maps some input IDs, so it gets input IDs as input, which simply are token IDs for some tokens. Let's say you have some input, the quick brown fox jumps over the lazy dog or whatever, and the token is just the ID 10,023 or whatever in your vocabulary. So as input, it just gets a list of these token IDs. And that's what these input IDs are. So it's just a list or a tensor of token IDs. And then the embedding layer also applies some positional encodings to these embeddings, which makes sure that the transformer model knows which token is in which position. Otherwise, if these positional encodings wouldn't be added, the transformer model wouldn't know, wouldn't have any information about the positions. Lastly, we do need to add one little thing. You can read up on the token type embeddings in the BERT paper if you would like. We just need to add it in this implementation to conform with the original BERT implementation. It doesn't really do much in this case. It's just there, so we get the same outputs. And then there's some layer normalization, which is applied to stabilize training. It just normalizes the output. So what does this look like in code? Here, let's define our embedding class. Again, just a child class from our module. And in the constructor, we receive the configuration, which is from Hugging Face, a BERT config file. This, not config file, it's just a configuration instance, sorry. And this instance contains the parameters, how our BERT model should be parameterized. For example, it contains the vocabulary size, how many tokens does the vocabulary contain, and for example, the hidden size, which just dictates how big or how many entries a representation vector per token has. And we can use these to initialize our different parameters or different layers and things like that of our model. So the first thing our embedding layer has is the word embeddings. These simply map token IDs to an embedding vector. So it has the shape configuration, or it has the shape vocabulary size times hidden size. So for every single token in our vocabulary, we have one vector of whatever hidden size dimensionality that can be accessed for every single token. The second part is the position embeddings. This is the same concept, except that for every single position, and we need to provide some maximum position encodings. So for example, for BERT, it's 512. For all 512 positions, this just contains a vector that is supposed to encode the position of a token. And then we have, as mentioned, these token type embeddings. We can ignore them for now, and some layer normalization that's applied on the output. And how does the forward function look? In the first step, we just grab, or as input, we get the input IDs. So this is a tensor containing the token IDs from our input. And the first step we do is we grab some position IDs, meaning this torch.arrange function, just if we have an input that's 32 tokens long, this will just be a tensor from 0 to 31. It just, some position indices. And then our hidden state, this is the representation vectors that we'll be passing through all of our layers in our model. Our initial hidden state will simply be the word embeddings, so the vectors for every single input ID, plus our token type embeddings, plus our position embeddings. So for every single token in our input, we'll grab its word embedding, and then we'll add the token type embedding and the position embedding on top. And then we apply our layer normalization, and that's everything that our embedding layer does. That's pretty much it. Okay, so as our output, we have our initial hidden state. These are some static word embeddings plus the positional encodings. How do we get contextualized embeddings from this? So how do we let other tokens attend to one another and things like that? And this is where the transformer layer comes in. What does a transformer layer consist of? In the image above, we saw it has a multi-head attention and then a multi-layer perceptron part. And we'll take a look at both of these one after another. The first one is the multi-head attention layer. What does the multi-head attention layer do? It takes as input a hidden state, so this sequence of representation vectors for every single token, and it outputs the same tensor, or the same shaped tensor again, but it just lets every single representation vector attend to every other single representation vector in this input. So this is what attention pretty much does. And then it again applies some normalization and a skip connection just to stabilize training and things like that. Visually, this is also from just the attention is all you need paper. I'm sure, or assume many of you have seen this graphic. The input, the hidden state, is first split into query key and value matrices, which are then split into multiple heads. We will take a look at how this looks in PyTorch in a second. And then per head, we do scale dot product attention. This is what scale dot product attention looks like. We just multiply the query and key matrices with one another. Then it's scaled down by some dimensionality. We can apply some optional masking, then compute probabilities. These probabilities then contain how much a token from the sequence attends to all other tokens in the sequence. And then this matmul, this final matmul, actually is the attention. So it then builds a, or the attending part of the attention. So it, depending on the probability distribution of how much a token attends to another token, this is then multiplied with the values. So it builds a kind of weighted average over all the value vectors. That's the new representation for a vector. That's the quick rundown. If you need a better intuition, there's a ton of good videos online explaining what attention really does. Here we now just want to take a look at how to implement this with PyTorch. And so this is our multi-head attention layer. Again, the same process. We have a module that is a child of torch.nn.module. It gets our configuration as input in the constructor. And then there's a couple of parameters we need to initialize. The first three, or these are just some helper configurations. We'll look at them later. But the first three here are our query key and value projections. This is how we obtain these query key and value matrices. So we take the hidden state and just apply linear layers to these that project the hidden state into a different, into different matrices, just a plain linear projection. Then we have a final output projection. That's not in the image, but that's a transformer layer, just projects the output one more time. And then we have layer normalization that's applied in the end as well. How does the forward function look like? As input, we receive the hidden state. This could be the hidden state from embeddings or the hidden state from a previous layer, whatever. And an attention mask. The attention mask pretty much just contains if we have two sequences, one, for example, is 128 long and one only 64 tokens long, then we want to mask out the final 64 tokens of the second implementation, because the tensor always needs to have equal shape. So then that just makes sure to mask out the final tokens. Okay, first step in our forward pass here is to grab our query key and value matrices. So we process our hidden state using the three linear layers. The next step is we split these matrices along the attention heads. So what does the shape of the hidden state or the query and key value matrices look like at the moment? The original shape is batch size, so we could have multiple sequences at once. That's what the B stands for. Then we have a sequence length. That's the number of tokens in our sequence. And then our hidden dimensionality. In this case, this is supposed to be in brackets. So we have, in BERT, it's 768 dimensions in this shape. And what we do with this is we rearrange this such that we have a batch size first, then a number of attention heads, which we set here using our H. So H is equal to a number of attention heads. In the official BERT implementation, it's 12. So we have a batch size times the number of attention heads times the sequence length and then the dimensionality that remains. So this is what multi-head attention is. We just simply split our hidden states into 12 different hidden states, or into the number of attention heads that we have. And this is what this rearrange does. This is the multi-head attention part of multi-head attention. All right. The next step is we just compute attention. So this is, we can go through this slowly, but this is pretty much the operation that's defined above. We just multiply our query matrix with our key matrix, which gives us some attention weights. This is the scale part. Then we do the optional masking part, where we do some mask filling using our attention mask as input. Then we apply the softmax, getting a probability distribution per token, and then we do our final multiplication with our value matrix. So query times key, scaling, masking, softmax, and then the final matrix multiplication. And this is exactly what happens here. So query times key, scaling, masking, softmax, and then our final matrix multiplication. That's all the magic that multi-head attention pretty much does. In the final part here, we just rearrange our hidden states again to remove the multiple heads. So here we move our head dimension back into the final part, back into our full dimensionality. So now we again have a batch size times sequence length times whatever, 768 dimensional vectors. And then we apply our final linear layer, just another linear output layer. And then here we do this layer normalization, and in this case here in the middle, our residual connection. So we add our input hidden states that we've stored up top here. So we just stored the input hidden state here, and we add this back on top. This stabilizes training and avoids some so-called vanishing gradients. So if we scroll back up top here real quickly, this is what our multi-head attention layer does. We do multi-head attention by first splitting into query key and values, do multi-head attention, and then we do our residual connection and normalization. Okay, this is our multi-head attention layer. Our final part of BERT is just a plain multi-layer perceptron. This just takes our hidden state and then applies an MLP to it. What does this look like? Same process as before. Initialize a new or create a new MLP module. And this just contains two linear layers and some layer normalization and an activation function, in this case, the GELU, Gaussian error linear unit, as our activation function. And the forward function simply applies all the layers after one another. There's no real magic to it. This is just a very simple, generic multi-layer perceptron, except in the end, we again have layer normalization and our residual connection by just adding the input hidden state to the output hidden state. All right, this pretty much gives us our BERT model, or our BERT layer for now. So as the first part, we can now define ourselves a BERT layer, which simply consists of a multi-head attention layer and an MLP layer. And our BERT layer then simply calls both the attention and the MLP layer one after the other and returns the new hidden state from that. From our BERT layer, we can now create our BERT model. What does the BERT model look like? We have a couple of things here, and our BERT model actually is a child of a pre-trained model. This is a class from Hugging Face Transformers. This makes it a bit easier to load the model and integrates it with the Hugging Face hub and things like that. And then we add a couple of options or attributes to make it easier to load the model. But in the end, our custom BERT model is simply our embedding layer we defined up top, and then our layers is a module list, which just means it's a list of modules in PyTorch of multiple BERT layers. And depending on our configuration, however many layers we have by default in BERT base, this is, for example, 12 layers. So here, this is just an embedding layer and our 12 BERT layers. And the forward function for our custom BERT model simply calls our embedding layer and then iteratively calls all our BERT layers one after the other. And our hidden state is simply the final hidden state after our last layer. I hope this kind of, it may look a bit complex for now, but if you take a close look, it shouldn't hopefully be too complicated. But yeah, that's all in a sense what a BERT layer does. And now we can just use the Hugging Face hub to load the weights for a pre-trained BERT model into our custom BERT model. We can use the from pre-trained method. If anyone has already used Hugging Face transformers before, you should be familiar with the from pre-trained method. We do need to do some weight conversions because the official Hugging Face implementation renames some layers and things like that. These are just some regular expressions that map some names between the different layers. We rename some stuff to make it easier to read, but in the end, that doesn't really change much. So we can run this, and what PyTorch then outputs, or what transformers then outputs, is we have a custom BERT model. This is our defined BERT model we defined above that consists of an embedding layer, and in this case, 12 BERT layers, which each consists of a multi-head attention layer and MLP. And we've now loaded all the weights from the official BERT-based uncased model from the Hugging Face hub. Yeah, we could use our custom BERT model now. For example, we can load the tokenizer from Hugging Face and tokenize some text. For example, the quick brown fox jumps over the lazy dog. And this will tokenize our text. If you're familiar with BERT tokenization, the first token is the so-called CLS token, and the final token is so-called separator token. But the other tokens in this input are just exactly our texts. So this is the quick brown fox jumps over the lazy dog, period. So this is the token IDs for our text that's been tokenized. And now in this part, we call or use the input IDs and the attention mask that our tokenizer has output to run our custom BERT model and just feed this in. And what we get out is our output hidden state, which now contains, for all the 12 tokens in our input, a 768 dimensional vector, which are our contextualized token embeddings for this input. And just to make sure that our BERT model actually is the exact same as the official BERT model, let's import the BERT model from the official transformers, or let's import the official transformers BERT model and also call the from pre-trained method, do the exact same call on the input IDs and the attention mask with the official BERT model. And then here with torch.allClose, we can compare the final hidden state of the official BERT output with our hidden state. And if this gives true, then that means every single value in the hidden state of the BERT model and our BERT model is very, very close to one another within floating point precision. So we've now re-implemented BERT. This gives us the exact same outputs as the official BERT model. Okay, going from here, now we've seen what the BERT source code looks like and how the model is built. What if we maybe want to make some modifications? So for example, what if we don't want a sequence-to-sequence model? So that gives us, we give an input sequence and then we get a contextualized token embedding for every single token in our output. What if we want a single embedding vector for every single input sequence that we give? So for example, we have some input tokens down here, and in every single layer, the number of vectors gets reduced. And this could be useful, for example, for sequence classification, where you just want one output vector to use for your prediction and things like that. How can we achieve this? One way would be using convolutional pooling. So to reduce the number of vectors in the hidden states, we could apply convolutional pooling that takes a couple of neighboring tokens, let's say 2 neighboring tokens or 2 neighboring vectors, and just computes the mean between 2 neighboring vectors, and that's the new vector at that spot. And then we, with some stride, jump into the next window. So kind of a convolutional mean pooling, which moves the window along. And this is what this function does. I'm not going to go into too much detail. It's a bit complicated because we have batched inputs in this case, so we can have multiple sequences. So it does a bit of complicated stuff to ensure that we don't include masked inputs in this mean convolutional pooling. But if we run this model and run this code and initialize this model, we can quickly demonstrate how this works by, if we, for example, have a batch size of 2 and a sequence length of 64 with a hidden dimension of 768 values, so 768 dimensions per vector, then we can initialize an input and initialize a mask where we then just mask out every from half for the second sequence. So the for the second sequence in our input, the 32, only the first 32 tokens actually should be involved in the attention. This is what this is supposed to demonstrate. So this is our hidden state at this point. We have 2 sequences, in total 64 tokens, or a maximum of 64 tokens per sequence with 768 dimensions per token. And then this is our mask. So this means every single token in the first sequence should be involved in the attention, but only the first 32 should be involved in the second sequence in the attention. The others should be masked out. If we now create a pooling, use our masked average pooling layer, and say we have a kernel size and a stride of 2, this means we always pool 2 neighboring vectors and then jump 2 vectors across and pull those 2 neighboring vectors. And this should, as a consequence, have the sequence length every single time. So if we always combine 2 vectors with one another and get one output vector, we should always get half the sequence length from our input. Now this is what we can see here as our input shape. We had a sequence length of 64 vectors. After applying our masked average pooling, we now have a sequence length of 32. So we only have 32 vectors with every 2 neighboring vectors having been computed the average between 2 neighboring vectors. Okay, let's add this custom pooling layer into our model. I just called this a sequence BERT, and we create a new configuration because now we have 2 extra parameters, namely the kernel size and the stride. And this we just have a child from the original BERT config, a child class from the original BERT config class, and just add this kernel size and stride to it so we can parameterize our kernel size and stride as well. And as a next step, we need to add this custom pooling operation into our BERT model. We could apply this in numerous locations. Just for simplicity, let's say we apply this after every single normal BERT layer. So here in this case, our sequence BERT layer is just a child of our original BERT layer we would find above, and we additionally add a pooling layer. And what we do is we call the forward function of our original BERT layer, and then just apply pooling on the hidden state output by our original layer, and then reducing the sequence length by half in every single layer. And that's what we output. That's our change that we do. Now we can define our sequence BERT model. That's just the same custom BERT model, but instead of using the BERT layer, we use the sequence BERT layer. Other than that, it's the exact same thing. Well, the one thing that does change is that since we're reducing the sequence length every single time, we also need to update the attention mask in every single layer, and we need to feed this through as well. So if you were keen-eyed in the previous normal custom BERT model, we only get an output of hidden state. In this case, every single layer outputs a hidden state and the attention mask, because that needs to get reduced as well. All right, just a quick note on what would happen for a 12-layer model. If we have 12 layers and we have the sequence length every single time, then a sequence length of any sequence that's below 4096 tokens should always be reduced to a single vector, because 2 to the power of 12 with 12 layers having every single time, this should be reduced. However, since our positional embedding layer only takes a maximum of 512 tokens, we can be sure every single sequence we give as input into our model will always be reduced to a single vector. And to as an example, to see the effect of our new sequence BERT model, here we create an instance of our model from the pre-trained BERT based on case weights, and then give a very long example lorem ipsum text just to make sure we have 512 tokens, and then feed this text into our custom original BERT custom model and print the shape of the hidden state, and our sequence BERT model and print the hidden state. And here we see our original BERT gives us exactly 512 tokens, or 512 vectors for every single token, but our sequence BERT model actually gives us one output vector. This reduced the contextualized token embeddings to one sequence level embedding vector, just by pooling the embeddings in every single layer. Note that, again, in this case, in experiments, I've built and tried and tested this model a bit. You will need to pre-train or fine-tune this sequence BERT model. This will not work well out of the box because BERT is not built for pooling inside of the layers. If you want to do this, make sure to pre-train or fine-tune your model. This probably won't work well out of the box. Yeah, that's it from my side. A quick introduction into PyTorch, and then how BERT models work in transformers, and then how you maybe could modify a BERT model as an example. Hopefully you learned something, and yeah, if you have any questions, feel free to ask them. Thanks for listening.
Thanks, Ferdi.